All right. What I'll do is I'll start where Oyojo just left. So as you can, I have already shared my screen. So if I'm not mistaken, you're already seeing what you should be seeing in Mitacho Rohanfi. And I'll continue from there. So I still have our good old laptop. And I guess Oyojo left with the BigM two-phase stuff. So I'll continue from there. By the way, in the meantime, if you need to say me anything, you can always raise your hand. I put the participants on here, so I'll try to see it. And you can always try to put a chat somewhere. I didn't open it yet, but if you want, I can also open the chat. Where is it? Hold on. No. Okay. Let's try with the raise hand thingy because I can't see the chat anymore. All right, and we are 105. Okay. Yeah, nice, right? Okay, so let's see. Now, okay, it's not easy to come to the this stuff, but all right, I'll try to open my. I'll try to be on the topic. So. Now, remember the simplex algorithm. Simplex actually works with basic solutions, right? Basic feasible solutions. All the examples that you had up until now always had a starting BFS ready available for you. There was always an identity matrix in your A hidden in it, and you would always go with it, right? You always had slacks or any normal variable with just one there. So you always had an identity hidden, and you started with that up until now. But of course, there will be situations where the initial starting BFS is not that apparent. So you may need to find how to start your simplex because it does require an identity to continue to optimize. But as I said, you need to have an identity to start it. So what we're going to do is there are two alternative methods for you to utilize if there is no identity hidden in the original problem. Okay? BigM is one alternative, and the other alternative is the two-phase method. We'll start with BigM. Normally, the simplex iterations are pretty much the same in both of those two methods. They have slight changes. So I'll start with the BigM first. Okay, so we have a LP that's shown in here. All right, we're going to minimize something subject to, we have 3 constraints and 2 variables, as you see on the board here. Okay. As you have already studied long before, you need to convert this to standard form first, right? But okay, so we go to maximization first. Minimizing something is equivalent to maximizing the negative of it. So we're going to maximize minus z, which is minus 2x1 minus 3x2, and the constraints are the same. Then we have to convert everything to equality form. Our row 0 is as shown in here. Hold on. Okay, and let me change the color. All right. Our row 0 is, as you see in here. Now, the first row was a less than or equal to, so we put a slack. The second row was a greater than or equal to, so we had to put an excess variable in it. Now, our thingy is in AX equals to B 4. Now, normally, up until now, you had 3 slacks in here so that you started your simplex. This time, we don't. So we need to introduce, that's what we do. We introduce artificial variables. They're not real variables. We just put them in to start the simplex algorithm. Then we're going to trick simplex, actually, to get rid of those variables during its original iterations. Here's what we're going to do. So I already have an identity. I have 1 slack, right? So I can use that. But I don't have a slack for the second and for the third constraint. So what I do, I make up 2 variables, 2 artificial variables. I just made them up, okay? A2 and A3. They don't appear anywhere else. So in the A matrix, now I do have my identity. I have a 1, 0, 0 here. I have a 0, 1, 0 and 0, 0, 1 for A3. All right? So now with these two additional variables, I can start my simplex algorithm because now I have my identity in it as if they were my starting BFS. But be careful, these are not real variables. So I have to trick simplex so that the algorithm itself gets rid of those variables. After a couple of iterations, if I can get rid of these variables, now I will have a BFS in my hand with my legitimate variables, right? How do I do that? Now, if I put very large costs for these artificial variables, then the algorithm, during optimization, the optimization itself will try to get rid of these variables. That's what we do, all right? So if it's a minimization problem, we put them as a plus. If it's a maximization problem, we put them as a minus. Just the idea. I'm going to utilize the optimization to get rid of those artificial variables. Well, how do I get rid of the artificial variables? Kick them out from the basis, right? If I can do that, I'll have a normal simplex table with legitimate basic variables, right? So that's what we're going to do then. I have two artificial variables for the second and third constraint because I do not have a constraint for, I do not have a unit vector for my second and third constraint. So I put artificial variables for those two constraints, okay? Now, I am supposed to add very large costs for those artificial variables in my row 0, and that's how it is, all right? So now I converted this, so now I have it. Be careful, look here. Now my artificial is also in my objective function, all right? Now I will convert this to the simplex table and perform the simplex iteration, as I always did. Let me pause a little bit because since I don't see your faces, I don't know if you can follow or not. So if you have any questions, please raise your hand. If not, I'm continuing. Any questions? Apparently not. Everybody is mute so that you can all hear me better. Okay, then I go on. Now, I repeat myself, but that's the motivation is then with the help of these very large multipliers in the row 0, I'll try to get rid of these artificials. So this is my first simplex table then, right? Remember, I have S1 for my first row because it was a legitimate variable already. For my second row, you see I have my artificial 2. And for my third row, I have my artificial 3. Now, be careful. You remember row 0? Those artificials had multipliers, right? So I'm supposed to have them in row 0 too. Now, there is one important thing that you should never forget. Now, in the basic feasible solution in a legitimate simplex table, these are not allowed, right? If this is a basic variable, row 0 coefficient should also be 0. So, well, I can still utilize elementary row operations and get rid of these guys from here, right? Because I don't want m there. They're supposed to be 0. How do I make them 0? You multiply this row with minus m, and you multiply this row with minus m, and add them up, right? That's what we have done. And as you see now, we have a legitimate simplex table, right? Nothing changed underneath here. But row 0 is now minus m times this and minus m times the other one. So we have a minus 30m in the row objective function portion. And now every basic variable has a 0 in the row 0 coefficient too. Okay? Any questions now? Or are you following me? Can somebody please say anything with, okay, hi, Irem, let me unmute you, okay? Is everything fine? Can you hear and can you follow?
Yes, I hear. Can I ask you something?
Sure.
Do the big M's have to be the same or can they be different?
That doesn't matter. It's easy if they are the same for you because they're like infinity. So infinity and 2 times infinity doesn't make much of a difference. These M's are not like the M's. in the binary formulations, we allow the different m's, and then I want you to find those m's. They were 2, 5, 8, right? In those cases, we were finding a good enough m. This time, we're not going to solve for m. We're just going to think in our mind that those are very large numbers, and the simplex will kick them out of the basis. Okay?
Okay.
All right. Thank you, Irem. All right. Okay, then what I'm supposed to do, I'll do more normal simplex iterations. As you see now, most negative variable in the row 0 will be my entering variable, right? So x2, because, I have 2 negatives in my row 0. x1 also has a negative coefficient, but minus 4m is supposed to be larger than minus 2m. So we start with the most negative, which is x2. x2 is entering. I'm applying my ratio test. And as you see, A2 wins. So in my first iteration, I'm kicking the artificial variable 2 out of my basis. It becomes non-basic, so its value becomes 0, right? So I do my iteration. Be careful. Once an artificial is out of the basis, I can immediately forget about its column. You don't need to update its column, okay? Because the guy is already out of the basis, okay? So I performed one iteration. You do all the simplex iterations. I'm not going through them because you already are solving a homework about a simplex, but if you have questions, you can still ask. So I performed one iteration. Now I have 2 legitimate variables in my basis, S1 and X2, right? And now but still I have one more artificial variable in the basis. So this is not still a legitimate simplex table for my original problem. Okay? Any questions? I'm waiting like 1 minute if somebody wants to figure out how to raise the hand. If not, I'll go on. All right. The next iteration, I still have negative variables in my row 0. Most negative is the variable for x1, row 0 coefficient of x1. So x1 enters to the basis, and if you do the ratio test, A3 is the winner, and A3 leaves the basis, right? Which was my second artificial variable. So my next table will be free of my artificial variables, and I'll be done. I will have a legitimate simplex table in my hand. Let's see. Now both of the artificials are out of the basis, and be careful, in the previous iteration, I did see m's again in my row 0, including this guy, right? But now in my next table, once artificials are out of my basis, m's are also out of my row 0, okay? Be careful with that. I'm done with all those m's. Fine, great. All those artificials are out now. I don't need to bother with them anymore. My first slack variable, x2 and x1, are my basic solutions. Now, if I had known these at the very beginning, I can create the simplex table but now I utilized my artificial variables to help me through the process. Now I have a legitimate simplex table. I can utilize and use the original simplex algorithm. Now, who can tell me what is my next move going to be? All right, Simge is trying to say something. Yes, Simge? Hold on. Okay, now I unmuted you. Say it again. Oh, sorry. Yes, Simge, can you say what you...
I didn't follow. How can we get rid of the M?
We didn't. The algorithm itself, I mean, we just performed elementary row operations because now x1 is entering and a3 is leaving. So this will become a 1 and these will become a 0, right? When I do all those iterations, all of a sudden, because all artificials are out of the basis, actually, m's are also out of the row 0. It wasn't on purpose, but it always happens. If your artificials are out, your m's are also out from your row 0.
Okay, thank you.
You're welcome. Hold on. Lower your hand. All right. Now let me bring you back to my question. I was asking, so what is my next move? What does this table tells you? Come on. All right, Vasik. Hold on, I'll unmute you. Hold on. Yes, Vasik? Oh, come on. I'll do that. Yeah. Yes, Vasik?
All right. So from this stage, the next step would basically be to find a possible feasible solution for this.
Yes, that was my question. So what is your next move?
We would break this. We would firstly write it in the format of AX equals to B, in which we'll identify the.
It was all. No, this is still in AX. This is a legitimate simplex table. So who enters, who lives is my question. If you don't have an answer, you can lower your hand and I'll.
Okay.
All right. So what is the next move? Who enters and who lives? Come on. Somebody. What was the rule to enter? What was the rule to enter? I don't see any hands. Irem? No, hold on. I'll unmute you. Yes, Irem? Huh.
Ratio test, maybe.
Enter. How do we enter? Which variable is going to enter?
Wait a minute. I don't know.
Okay, lower your hand.
Okay.
All right, let me see if Celine wants to say anything. Yes, Celine?
The rule to enter is to have a negative coefficient in the row 0.
Exactly. And
we don't have any of those.
Yeah.
So we won't have an entering variable, I guess.
Exactly. And what does this mean?
So we reached the optimal solution and we can find the solutions for X1, X2, and S1 at this point.
Exactly. Thank you very much, Celine. So this table I'm muting you again. So our motivation was just to find a starting BFS, but as you have just seen, we have actually, during the process, we have actually reached the optimum solution, right? There is no entering variable. All row 0 coefficients are non-zero, are positive, yes? Then this is our optimum solution. And here you see the optimal values. Both x's are 5. Our first slack variable is 1/4, and our objective function is -25. Okay? Be careful. This was we converted this, so the original objective function is minus of it. So our original problem's objective function is 25. There are some remarks here that I want to discuss. The first remark says, I have already said it, but these are also written in here. Once an artificial variable is out of the basis, which means once an artificial becomes a non-basic variable, it will never become a basic variable again. No way. Okay? Because of its objective function coefficient. It will never be profitable to put it in the objective function. If it becomes, then you made a mistake. Go back, check your errors, check your calculations. Once an artificial is out of the basis, it never will become basic again. So for that, that's why we can delete the column corresponding to that basic artificial variable, and we're not updating its values while we're updating the simplex table. Okay, that's one. And the second remark is, again, I have already utilized this fact. Minus 6m is smaller than minus 3m, so most negative is coming with that issue. All right. Let's solve another example with the BigM method. Okay. Let's see. Now the headphones and my glasses doesn't work well, but let's try. All right. So we have another example. Any question? Because I have actually explained all the basics regarding with the BigM method. Now I'll solve another problem. Let me repeat myself, what we did from the beginning. As I said, if the original problem has a hidden identity in it, we're saved. We don't need to bother with BigM. We put the table, we see the identity, we go for it. We start our simplex with the identity. If there is none, which was the case in our example in here, then we need to we can utilize a method that we call BigM. What we do is we put artificials in the required rows, which do not have an unit vector representing them, okay? We put enough artificials. As you see, we didn't put 3 artificials in the previous problem, even though we needed 3, because there was already a slack variable that we could utilize. So what we did, we put 2 artificials because there were 2 rows which do not have units, and then a unit vector. And we put very large costs for them in the objective function, and the simplex itself actually get rid of them during the iterations. Well, we were lucky. Once we get the BFS, our BFS was optimal. It doesn't have to be. If here we had a negative coefficient in row 0, we would enter it and leave the rest and do the standard simplex that we keep on doing. Okay? That is the main steps of the algorithm. Do we have any questions? If not, I'll go to the second example. Any questions? Okay, second example then. We're maximizing x1 plus x2 subject to 2 constraints. Let's see. Let's look at the now if you look here, there is no slack. So if I convert this is going to be x1 minus x2 minus e1 equals to 1 minus x1 plus x2 minus e2 equals to 1. I do not have a hidden identity. That means I have to have 2 artificials in here and in here to start my simplex algorithm, right? That's what's happening then. x1, x2, xs1, xs2, and I have 2 artificial variables. All right? Now, I convert it. I put my everything. I have my ones in here, so I do have my identity. And these artificial variables will have very large cost because original problem is maximization. This is row 0. They come with a very large cost, right? So again, I don't want this. This has to be 0. This has to be 0. So I have to convert my row 0 to a proper form, which means minus m and minus m, right? Which brings me to my next table. Now this is a legitimate simplex table. I have my identity and I have my zeros in row 0. Okay, I'll do my simplex iteration. So which variable is entering? Which I showed it to you already. But now I have 2 negatives, all right? It doesn't matter which can do. So let's start with x1. Let's say x1 is entering. Both are fine. You can choose one arbitrarily, right? Okay. So if x1 is entering, I have to do a row ratio test. Now this is not valid because its coefficient is negative. So I only have one option. A1 is leaving and x1 is entering, right? I'm supposed to do elementary row operations so that these become a 0 because now x1 will be basic. And this is my next table then. x1 is in the basis with an identity column, and my second basic variable is a2. I have deleted a1 because I kicked a1 out of my basis, okay? My next iteration, most negative variable is x2. So x2 is entering. Who's leaving? I have an entering variable, but I do not have a leaving variable. Now, it says infeasible here, but remember the simplex that you have seen, the original simplex? When there is an entering variable, but no leaving variable, infeasibility was not the thing we deduced, right? When there is an entering variable, but no living variable, that would mean that our problem was, let me see the hands. I'm still going to do the participation. So, all right, Gülin, I'm going to unmute you. You were the first. Hold on. Yes? Unbounded. Very good. If the problem has a, hold on, I have to mute you again. So if the problem has an entering variable, but no living variable, then the problem was unbounded. So why do we have written that the problem was infeasible in here? Because if you have a simplex table in your hand, the problem that you're trying to solve supposed to be feasible because the simplex table has a basic feasible solution that you're going with, right? By definition, it has a feasibility in it. But this is not the original problem. This is the artificial problem I made up just to start my original problem, right? So with this artificial problem, my artificial problem is unbounded with all those BigMs. Yes, but this is not my original problem. Since I cannot kick those artificial variables out of my basis, the only thing I could deduce from this table is that my original problem was actually infeasible. All right? Okay, so let's go over some remarks that we have all gathered for you. The method, the steps of the method. I have to modify the constraints so that everything becomes an equality. Then we put our slacks, excess, whatever, all right? And then if we require, we put artificials for the constraints that we need to. Then we pick M's, and for those artificial variables will come to my picture with big M's. Depending on if it's a minimization or maximization, I will try to kick them out from my basis. So I will put them with the appropriate sign to my objective function so that simplex will try to get them out from my basis. All right? And the rule, okay, there is a question. Hold on. Yes, Vasik?
I have a question. Is it only that we add artificial variables for the excess that we have, or do we?
Or equalities, yeah.
Yes, or do we add it for the slack as well?
If there is a slack, you don't need to put an artificial there because the slack already has a unit vector assigned with it. So it's a legitimate unit vector. I don't need an artificial for a constraint which has already slack variable in it. But the other constraints, which are excess funds or just equality in the original form, do not come with a unit vector assigned to them. So I need the artificial variables for them. Clear? All right, I'm muting you. Okay, so let me go on. And the rule then, at the end of the BigM method, the first example was the good scenario. I kick all my artificial variables out of the basis, and I had legitimate basic variables that I could go on with. And if it is not optimal, you continue with the legitimate simplex that you already do. You have to be careful in one situation if you're applying BigM. The method, the simplex, can tell you that the problem is unbounded, but there you have to be careful if you still have artificials in the basis or not. The unbounded problem with artificial variables doesn't make anything because it's not feasible yet. The very first rule is we have to first be feasible, then we can think about unique optimal, alternative optimal, and unboundedness. So even if you're applying BigM, and even if the algorithm says, you know what, this looks like unbounded, you first have to check if it is feasible or not. And if my artificials are still in the basis, that means I'm not feasible yet, which means the original problem was actually infeasible. Okay? Any questions? All right. Now I have a couple of questions in here. First one says, If all artificial variables in the optimal solution is 0, the solution in your hand is optimal. That was our first situation, right? In the example, I solved my simplex. My artificials were non-basic. They're all 0. So my solution is optimal. If I optimized my simplex, but there are still artificial variables in the bases. It doesn't have to be unbounded all the time, by the way. The simplex can stop saying that, you know what, this is optimal. But in that optimum solution, you may still have some artificial variables. In that case, your objective function will also have some m's in it. Well, that would mean that your problem is infeasible because you couldn't kick them out. You couldn't kick the artificial variables out of the basis. So even if simplex says this is optimal, the artificial problem is optimal. It's not your original problem. And my original problem can only be infeasible because the artificials are still in. I made them up, and apparently I cannot kick them out. Then original problem is infeasible. All right? The third remark says, I solved the problem with the artificial variables. The final table says the LP is unbounded. If the final table indicates the LP is unbounded and all artificial variables are 0, then original LP is, let me see a hand in here. If you can follow, you can answer this. My BigM simplex table stopped saying that it's unbounded. I check my artificials, their values are 0. What does this mean? Didem, I'm going to unmute you. Oh, hold on. I'm going to unmute you. Yes, Didem.
It is unbounded.
Then the original problem is also unbounded. Exactly. Very good. Thank you very much. I'm muting you too. If all artificials were 0, this is not the situation we had in the example. In our example, when it says unbounded, my artificial variable 2 was getting the value of 2. It was not 0. If it says 0 in here, I could declare that the original problem was unbounded, which is what this remark here actually says. Okay? Again, if the final table indicates the LP is unbounded and there is a positive artificial variable in the table, that means the original problem is actually infeasible, which is what our example has just did. Okay? More remarks. Any questions? Because I actually finished what I want to explain from BigM, but let me go with the remark also. For computer programs that you're going to be learning, like Excel, Express, Simplex, because you're going to hopefully learn those, it is difficult to determine what is that large M is. Okay, so how big M is going to be? What's happening? Okay. Okay. It's really not that easy to come up with a good, large enough number. Because if you put like 10 to the minus 9 and your normal numbers are 0.3 and 0.5, then you might start to get into some issues with your optimization solver. And that's why there is an alternative for this method, which we call the two-phase method. Okay? It's the basic steps is exactly the same, but it doesn't have BigMs. So there must be another trick to kick the basic variables out of the basis, because we utilize BigMs so that the simplex during the algorithm will kick them out of the basis, make them non-basic so that their values will become 0, because they're not legitimate variables anyway. Normally they have to be 0. So in the BigM method, we used very large multipliers to make that possible. In the two-phase method, we're going to utilize something else, which is the two-phase method.